So in this video, we're continuing our discussion of colligative properties of solutions. We started this in class the other day. We discussed the vapor pressure lowering as the fundamental colligative property. Colligative properties, you remember, were properties of solutions that depend only on the number of solute particles dissolved, not on the identity of the solute particles themselves. We suggested that vapor pressure lowering was a fundamental colligative property because it related directly to two others, changes in boiling point and changes in freezing point. So today we're going to look at those two properties as well as a fourth property called osmotic pressure. So let's begin with boiling points. We remember the definition of a normal boiling point. This is the temperature when a liquid's vapor pressure is equal to 1 atmosphere. Okay, liquids are evaporating. That vapor creates vapor pressure. When the pressure is equal to the standard pressure, that temperature is the normal boiling point. We know that when you dissolve a solute, the vapor pressure above that solution is lowered compared to the vapor pressure above the pure solvent. So therefore, if you're trying to achieve a vapor pressure of 1 atmosphere, the lowering of the vapor pressure will mean you have to raise the temperature even further to get the liquid to boil, to get your solution to boil. As a result, the boiling point of the solution will always be elevated. It'll be greater than the boiling point of the pure solvent. Okay, if you need to pause the video to continue taking down some of the notes, do so. Mathematically, we can describe boiling point elevation with this simple formula. Okay, it's got about 4 variables. The change in the boiling point, delta TB, also you look at that as the boiling point elevation if you like. It's equal to the boiling point of the solution, TB, minus the boiling point of the pure solvent, TB with a degree symbol. You remember the degree symbol refers to the pure solvent. That change in boiling point is equal to I times Kb times molality. The I stands for the Vant Hoff factor, and we'll discuss that in a moment. Kb is a constant that's different for different solvents. It's called the molal boiling point elevation constant, or simply the boiling point elevation constant if you prefer. Down below you see a table with different solvents, and for each solvent there's a particular value of Kb listed. The M in the formula stands for molality, which is one of our units of concentration. It's the number of moles of solute per kilogram of solvent. In fact, when I use this formula to solve problems, I will almost always take the little m in the formula and explode it into moles of solute divided by kilograms of solvent. The I was called the Vant Hoff factor. Now you remember that colligative properties depend on the number of particles created in the solution. So if you're dissolving a solute which is non-electrolyte, a solute which is molecular, okay, a covalent compound, then it does not break apart into any ions when it dissolves. Molecular substances, if you dissolve one particle, you'll get one particle floating around in your solvent. So for every mole of a non-electrolyte that you dissolve, you get 1 mole of dissolved solute particles. Therefore, for non-electrolytes, the Vant Hoff factor is equal to 1. If you have an electrolyte, so an ionic solute, one that breaks apart into ions, and that will allow the solution to conduct electricity, which is why they're called electrolytes. The electrolytes, we know, break apart into their ions as they dissolve. They dissociate. Well, the Vant Hoff factor is going to equal the total number of ions in the formula of that salt. Let's look at some specific examples. We see the first example, C6H12O6, is glucose. and that is, from its formula, carbon, hydrogen, oxygen, clearly just a covalent compound. It's molecular. Therefore, it will not break apart into ions as it dissolves. If you dissolve 1 mole of glucose, you'll get 1 mole of dissolved solute particles. Therefore, for glucose, the Vant Hoff factor is equal to 1. On the other hand, if you dissolve an electrolyte, sodium chloride, we notice that its formula has 1 Na and 1 Cl. So when you dissolve a mole of sodium chloride, you get 2 moles of particles in the solution. You'll get a mole of sodium ions, and you'll also get a mole of chloride ions. So because 1 mole of sodium chloride gives me 2 moles of particles in solution, its Vant Hoff factor, I, is equal to 2. For calcium nitrate, CaNO3 2, we can tell from its formula that when 1 mole of calcium nitrate dissolves, you get 3 moles of particles. You'll get 1 mole of calcium ions and 2 moles of nitrate ions. So since 1 mole of solute gives me 3 moles of particles, calcium nitrate's Vant Hoff factor is a 3. And for sodium phosphate, one last example, 1 mole of sodium phosphate will give me 4 moles of particles. I'll get 3 moles of sodium and 1 mole of phosphate. So for sodium phosphate, the Vant Hoff factor is equal to 4. So the value of the Vant Hoff factor, as you see, depends on the solutes. For non-electrolytes, covalent molecular compounds, I is always equal to 1. For electrolytes, you look at the number of ions in the formula of the salt. Now I should point out that those Vant Hoff factors that I've just described for the electrolytes are ideal because they assume that the electrolyte is completely ionizing. We know from the beginning of this unit that when salts dissolve, they dissociate, they break into their ions, but as those ions float around in water, we discussed this earlier, sometimes a cation and an anion will approach each other, even though they're hydrated, surrounded by water molecules. They may approach each other and rejoin in an ion pair. So you might get a sodium and a chloride that rejoin to make NaCl in water at any given point in the solution. Now that NaCl particle that's formed will get pulled apart again in just a moment, but then somewhere else an NaCl particle could form again. This is called ion pairing. Because of that, you don't actually have complete dissociation at any given moment in the solution. So the actual Vant Hoff factors will be less than these ideal values that we see here. Now, the charge on the ions affects the real Vant Hoff factor. If the charges on the ions are larger, so let's say a +2 ion versus a +1 ion, the larger charges will mean the phenomenon of ion pairing is more likely. As the ions have greater charge, they're more likely to form these ion pairs in solution. So the greater the charges on the ions, the greater the deviation from ideal behavior. So putting that into some quantitative form, for sodium chloride, we said its Vant Hoff factor should be a 2. The sodium and the chloride are +1 and -1, so there'll be some ion pairing, but not a lot. So you might get a real Vant Hoff factor of 1.9, for example. Calcium nitrate, on the other hand, has a 2 positive calcium and 1 negative nitrates. That 2 positive calcium means its ion pairing is likely going to be greater than that in sodium chloride. So its real Vant Hoff factor will deviate more. So instead of a 3, maybe now it's 2.7. For sodium phosphate, there's a 3 negative phosphate ion. The 3 negative ion means its ion pairing is going to be strongest of these 3 examples. So there, the deviation will be the largest. So instead of 4, its real Vant Hoff factor might be 3.2 or something like that. Now in a problem, if you're not given the real Vant Hoff factor to use, and you usually won't be, then you're going to just use these ideal values. But if a question did tell you the real Vant Hoff factor, you would understand, I hope now, what that means, and you would use the real value in your problem solving. All right, you'll notice from the table below, you don't need to copy the table because you have a table like this in your data booklet. It's at the last page of the data booklet. Each solvent has a different boiling point, a different Kb value, the boiling point elevation constant. They have different freezing points, and as we'll see in a minute, they have different Kf values as well, the freezing point constants. If you need to, pause the video and continue copying the notes. So freezing point depression. Mathematically, as we'll see in a moment, this is identical to boiling point elevation. However, the phenomenon is a little bit different. When a solution starts to freeze, it's the solvent particles which are forming a crystal lattice structure as they're solidifying. The solute particles usually don't fit into the crystal lattice structure. They're usually of different sizes, or they might be of different polarity, for example. So because the solute particles don't fit into the crystal lattice easily, the solid that's freezing is normally pure solvent. So as you're freezing salt water, the ice that you see will contain very little or no salt. It'll be pretty much pure water. Okay, this is referred to sometimes as the salting out effect. You're getting salt out of the water, and you're getting pure water in the form of ice as you freeze the salt water. The solute particles that are remaining in solution are becoming more and more concentrated because the solvent is freezing, so there's less and less liquid in the beaker, but you have the same amount of solute. As the solute becomes more concentrated, it physically starts to inhibit solvent particles from joining the crystal lattice. So basically they have to collide with the crystal lattice to freeze, but all these solute particles are in the way. That physical blocking or inhibiting of the freezing is what causes the freezing point of the solution to be less than the freezing point of the pure solvent. So this is called freezing point depression because the freezing point is lower than the freezing point of the pure solvent. Pause the video if you need to continue writing. So mathematically, the equation as I'm writing it here is identical to the equation we wrote for boiling point elevation, except the subscripts are changed from B's to F's, because now we're talking about freezing point depression. Now there's one thing to note though, the change in the freezing point will be, we always want to use a positive value, even though it's being dropped, which would lead by this little equation to a negative delta TF. Take its absolute value. You always want to use the positive change in the freezing point when you're using this formula. So for example, for water, its normal freezing point is 0 degrees. If you find that a solution freezes at -4 degrees, well, technically delta TF would equal -4. But for this equation, you would say delta TF is 4. You take the absolute value of that when you're putting it into the equation. It's still equal to the Vant Hoff factor, I, and it's the same factor that we just discussed, times a different constant, which again is based on the solvent that you're using. So this is the molal freezing point depression constant, Kf. It'll be given to you in a problem, or you can look it up in your data booklet at the end. And then the molality again of the solution. So the moles of solute divided by the kilograms of solvent. Now, although we can use these two formulas for boiling point elevation and freezing point depression, we could use them to calculate boiling points of solutions or freezing points of solutions. That's really not what their main use is. They're used instead to calculate molar masses for solutes. So what you would do is you might have a solute whose identity you're trying to determine, you would make a solution with your solute, measure the freezing point of the solution or measure the boiling point of the solution, and from that information you'd work out what the molar mass of the solute was. Can you take the equation you see here and start with the formula delta TF equals I times KF times molality? Can you rearrange that formula to solve for molar mass? To do that, you want to play the same kind of tricks that we played with the ideal gas law earlier. You want to note that molality is moles of solute, so N subscript solute, divided by kilograms of solvent, so kilograms subscript solvent. Then you can take your moles of solute and you can change that into mass of solute divided by molar mass of solute. Now you can rearrange the equation to find molar mass of solute equals. So see if you can do that. Pause the video and see if you can isolate molar mass. In many problems, that's the kind of algebraic manipulation we'll do at the start of a problem if we're trying to find a molar mass. So pause the video and see if you can do that before continuing. The final colligative property is called osmotic pressure. It's one that you might be familiar with from your biology class. When you have a solution with separated from another solution or separated from pure solvent by what's called a semi-permeable membrane, you have a situation where osmotic pressure is going to be created. Osmosis, you remember, is the movement of water across the semi-permeable membrane from an area of low solute concentration to an area of high solute concentration. So what you have is what's called a concentration gradient, and I'm using a mouse to draw this, so forgive me for the horrible writing. But it's sort of like if you think of a fulcrum with a lever on top, so sort of like a seesaw on a playground. At one side of you have a low concentration, at the other side you have a high concentration. So that's called a concentration gradient. Low on one side, high on the other side. The solution is trying to get rid of this gradient. It wants to have the lower concentration increase, so it wants to have the higher concentration decrease until they're equal. Then there will not be a concentration gradient. If there was no membrane present, then the most simple way for that to happen would be to use diffusion. The solute particles would move from the higher concentration area to the lower concentration area. That's diffusion. And as they do, the higher concentration drops, the lower concentration gets bigger, and your gradient will disappear. The problem here, though, is that we've put a membrane in the middle. So if you look at this U-shaped tube, and please draw it, okay, a U-shaped tube, there is a disc at the bottom, right here, that has a membrane, and that membrane is semi-permeable. Now in the diagram on one side it says dilute solution. Let's change that. Let's make this an extreme example and say on one side we just have pure water, so H2O. On the other side, so pure solvent. On the other side of that membrane you have a solution. That's a concentrated solution. Now when we say the membrane is semi-permeable, what we mean is that the solute particles in the solution are not permitted to travel across the membrane. It won't allow them to pass. But the water particles are able to pass through the membrane. So in that way it's permeable to water but not permeable to solute. So it's semi-permeable. If the membrane stops the solute particles from moving across, then diffusion cannot happen. So when you have this gradient with zero concentration on the right and some higher concentration on the left, diffusion cannot happen. So we cross out that possibility. So is there any other way to get rid of the gradient that we have? We have a lower concentration on one side and a higher concentration on the other side of that membrane. So we have a gradient. Can we get rid of it? Well, the water is able to move across the membrane. So what happens in osmosis is that the water travels from the lower concentration area to the higher concentration area. So water will move across this membrane in this direction from where there's zero solute to where there's the solution. As the water moves across, the solution becomes diluted, and so its concentration drops, and the gradient gets smaller. Now, if I asked you to predict what would be the end result of that process, you might, if you were thinking of what we saw in an earlier example, you might think that, well, on the one side of the membrane, there will always be pure water, and on the other side, there will always be, even if it's diluted, a solution. So you might think that there will always be movement of water across into the solution until the point where there's no water left. I can understand why you would think that if you were paying attention to the earlier discussion about two beakers under a dome. Well, what happens here, though, we have a different situation. As the water moves across the membrane, the left-hand side in this U-shaped tube gets higher, and the right-hand side gets lower. So what you have, in effect, should look familiar to you from our gases unit. You have what's called a manometer, right? So on one side you have higher water, on the other side you have less and less water, so you get a delta H, you get a difference in height between those two levels of water. So that delta H represents increasing pressure. The added weight of the water on the left side creates pressure, and what that does is you have water trying to move across this way because of osmosis, but that added pressure starts to force the water to move back the other way. And eventually, as the water keeps moving across by osmosis, eventually the pressure gets larger and larger until it equals the pressure of the osmosis. And at that point, the water molecules are moving across the membrane in both directions equally, and there's no longer a change in the levels of water. You've reached equilibrium. At that point, if you measure that delta H, you've got what's called osmotic pressure. Another way to say that is if you had instead, if you started to apply excess pressure, so let's take a piston or something and start applying pressure here, we could force that water to move back to its original levels until it's equal on both sides. If we do that, if we push it back to its original state, then the pressure we would need to use to do that is called osmotic pressure. A third way to think about it would be you could start with the original U-shaped tube and you could apply that same pressure at the beginning before the osmosis has happened. As you're applying that pressure right from the beginning, you're preventing the osmosis from happening in the first place. So there's three different ways of thinking about what osmotic pressure is. You can think of it as the pressure created when the osmosis happens and the system reaches equilibrium, the pressure by the differing levels of water on both sides of the membrane. You could think of it as the pressure you need to restore the levels to their equal heights on both sides. Or you can think of it as the pressure needed to prevent the osmosis from happening in the first place. Any one of those three descriptions describes osmotic pressure. Now the mathematical formula, well actually before I move to there, what would happen if you applied greater pressure than you needed to restore it? Or you apply greater pressure than you would need to prevent osmosis. If you apply a greater pressure, then you'll actually force the water to move across the membrane in the direction opposite of osmosis. So what you'd be doing now is called reverse osmosis. You're applying pressure, and that takes energy, to go against the direction that the osmosis is trying to move the water. The reason you would want to do that is you would take say a contaminated solution, or maybe salt water, and by applying pressure across the semi-permeable membrane, you could take the salt water and force it to move in the opposite direction, and you could create pure drinking water as a result. So that's one way of getting drinking water, removing salt from from salt water and getting pure water as a result. If you buy Culligan water at the store, it's usually called reverse osmosis water, okay, because you're applying more pressure than the osmotic pressure. Now the formula looks a little odd, I'm sure, but it actually is derived from a simple place. Okay? The formula for osmotic pressure starts with the ideal gas law, actually. P times V is equal to nRT. And again, forgive my writing, I'm using a mouse to do this. If you divide both sides by V, you'll get P is equal to, and you could write N over V RT. But N over V is the definition of concentration, isn't it? Moles divided by volume. So we could say P is equal to C RT. That's a valid way of writing the ideal gas law, P equals CRT. Now, if your solute that you're dissolving is ionic, then it will have a Vant Hoff factor that's not equal to 1. So we can throw a Vant Hoff factor into the equation to account for the additional particles as a result of dissociation. Now finally, this equation right now looks like the ideal gas law. However, we're not talking about gases, we're talking about a solution and osmosis. So what we'll do is we'll just use a different letter for pressure. Instead of the letter P, capital P in our normal alphabet, we'll use the capital P from the Greek alphabet, which is the letter pi. But just like our lowercase p looks the same as our uppercase p, the uppercase pi just looks like a larger version of the normal pi that you would write. So pi, osmotic pressure, is equal to I, the Vant Hoff factor, times your molarity, the concentration, times R times T. Now notice this C is molarity. It's not molality that we were using earlier. Just like the ideal gas law, we have the same restrictions. Temperature has to be in Kelvin. The value for R will be determined by the units of your osmotic pressure. If you want to use 0.0821 for R, then the pressure would be in atmospheres. If you use 8.314 for R, the pressure would be in kilopascals. Finally, before I turn you loose to do some problem solving, there's 3 other terms I just want you to know, and this is a direct relation to biology. We talk about solutions in biology as being isotonic, hypertonic, and hypotonic. If you remember that the prefix iso implies the same, that'll help you remember what an isotonic solution is. It's a solution where the concentration in the solution is the same as the concentration of a blood cell or some kind of membrane enclosed structure inside the solution. So usually in biology you're talking about cells that are in blood or cells that are in a solution. So the cell has a semi-permeable membrane around it. There's some kind of aqueous solution inside the cell, it's cytoplasm, and then there's solution outside the membrane. If the concentration outside and inside are equal, then the solution is said to be isotonic. If they're equal, then there's no pressure to perform osmosis. So there's no net movement of water across the membrane. A hypertonic solution, hyper means bigger, greater. Okay, if someone's hyper, they have lots and lots of energy. So hyper means greater. Now the solution's concentration outside the cell is greater than the concentration inside the cell. So because the concentration outside is greater, there's going to be a concentration gradient. And as a result, there's going to be osmosis across the cell's membrane. You remember that the water moves towards the higher concentration region, so the water here will move outside of the cell, and the cell is going to get shriveled up and shrunk. Finally, the solution might have a lower concentration than inside the cell. If you put a red blood cell, for example, into pure water, distilled water, then the distilled water outside the cell has 0 concentration of dissolved solutes, but inside the cell there's a relatively high concentration. So now osmosis is going to send water from outside the cell to the inside of the cell, right, towards the higher concentration region. So the hypotonic solution has a lower concentration than inside the cell. As the water flows in, the cell is going to get larger and larger and could actually burst. If you put red blood cells into distilled water, they'll actually explode. Okay? So isotonic, hypertonic, and hypotonic solutions. Be sure you know all 3 of those definitions and can apply them. So pause the video if you need to write down these last few notes. Then you'll be able to hopefully have enough to begin some problem solving with WebAssign. If you are struggling with some of the problems, just relax. We'll look at them on Monday, but be sure you've given them a good try over the weekend.